All right, this is problem solving session 1. We're going to go ahead and start with quiz 1-1 under files. So I will go ahead and pull that over so that we have a visual ref for it. Okay, are y'all able to see the Z board? All good? Sweet. So this is on fluids, of course. Let's go ahead and pull over our main equation of interest. So this is the Bernoulli equation, especially for students who haven't yet been to DL. This is the main equation we play with in the context of fluids. And that is that between any 2 points in a fluid system, in steady state or in dynamic equilibrium, the change in pressure between those 2 points plus rho, the mass density, times gravity, times the change in height between these 2 points, delta y, plus 1/2 rho, which is again the mass density, times delta of v squared. V here is the velocity, the speed of fluid flow at each point in the pipe, equals the energy given by any pump per volume minus a thermal dissipation term. The first thing, the I here, is the current. It's the amount of volume per time that is traveling through the area of the tube. The second thing is a resistive term. It refers to basically like how hard it is, how resistive the pipe is. So this is often, our little shorthand for this in Physics 7 is that the tube is a little rusty or rough. So there's like friction on the walls. Okay, I've got a chat coming in. Why is rho called mass density, and how is it different from density when both equal m over v? Good. So in the past, you've probably just heard of mass density as density. That's the typical way that, like, I think this is the first density that most people interact with and hear about. So a density in general is just something per volume, So the mass density, rho, is mass per volume. The energy density, which is the subject of, here we go, the subject of this equation, is energy per volume. So we don't have a symbol for energy density. I just say energy density is energy per volume. Thanks for the question, Ethan. So basically, I call rho mass density because it refers to mass per volume, and there are other kinds of densities. There are also things called, it's not outside the scope of the course, but there are also things called probability densities, certain regions in space where probability lives. If left unstated, should we assume the fluid is water and the density is 1,000? What I'd say is it should not go unstated. So if it does go unstated, I guess I'm okay with making that assumption. But overall, we'll be sure to state it. Yeah. Thanks, Sydney. Also, the density, make sure, watch your units, 1,000 kilograms per meter cubed. Okay. So there's our equation that we'll be mainly working with here. The other equation is one of continuity. So the continuity equation for fluid systems is this one. It is that if I have a pipe, the fluid entering the pipe must be the same, or the amount of fluid entering the pipe must be the same as the fluid exiting the pipe. In other words, I1 has to be the same as I2. What is I? I is the current, or some people call it the flow rate, if you like, but we call it current. So I is the area of the container times the velocity of the fluid. So the way that I think about this, like geometrically, is that there's some area, A, and there's a velocity, V, that the fluid is moving along. So I think of it as being almost like a measure of how long this little cylinder of water is that is traveling along in 1 second. So, okay. Hopefully that makes some sense. So it's a measure of how quickly water is flowing. So if my current is like 15 gallons per second, it means that 15 gallons per second are traveling through this pipe. More questions, more questions? Otherwise, we'll hop into the question proper. Okay, let's do it. So, read the thing first. A part of a fluid system is depicted here. The water is flowing to the right. Okay, it is water, nice. The fluid columns marked A, B, and C are places in 3 locations giving pressure gauge measurements. So each of these vertical columns is a pressure gauge. And this will be revealed in greater detail in the DL. I'll talk about why it is briefly here too. But the main fluid system is this lower part. That's where water is flowing. And these 3 pipes up top are giving us a handle on the pressure at the bottom. Okay. What is the equation? We got a question, sorry. What is the equation next to density P equals mv? Or rho equals m over v. So what I'm saying over here is that I have this other thing, energy density, which is energy per volume. So what I've tried to write here is E dot dense, D-E-N-S. And my handwriting is garbage. So feel free to ask similar questions if my handwriting is not clear. Thanks, Linda. Okay. We have fluid columns marked A, B, and C, giving us pressure gauge measurements. All columns are open to the atmosphere. So at the top of each of these tubes, I have atmospheric pressure. That's what that tells me. So if we have a section of a fluid system that is open to the atmosphere, that section of the fluid system is at atmospheric pressure. One way I think about this is PATM. One way I think about this is that if the 2 fluids had different pressures, so if the 2 fluids, when I say 2 fluids, what do I mean? Let's say that this gauge, I'll just draw a gauge up here. If I had a gauge that was had water on the bottom and air on top, so this is supposed to give me an idea of pressure somewhere in my fluid system. If the air were at a lower pressure than the water at this interface right here, at the point where they meet, then the water would push up into the air. And if the air had higher pressure than the water at this interface, then the air would push down into the water. So the fact that it's at equilibrium, namely that the 2 are balancing each other out, that the air interface and that the air side of the interface and the water side of the interface aren't able to bully one another into moving, indicates that the air-water interface is at atmospheric pressure. The water at this point is at the same pressure as the air, atmospheric pressure. Okay, so there's a height difference only between points 1 and 2, and it looks to me like point 2 and 3 are at the same height, so between 1 and 3 by extension. There is no resistance in the pipe between points 1 and 2, and there is a non-zero resistance in the pipe between points 2 and 3. The area of the pipe is 4 centimeters squared and is constant throughout. Okay, so real quick, I'll let you know what I'm reading when I read that. So this sentence here is a more complicated one. This sentence here, this final sentence, the area of the pipe being 4 centimeters squared and constant throughout, this is a statement to me that the speed is constant throughout. So that's because of continuity. Continuity says that the current into a section of pipe has to equal the current out of a section of pipe. In other words, that the area in the first section, or in the entrance, say, times the velocity through that section must be equal to the area through the exit times the velocity through that exit. So if the area is constant, the area is the same. I'll just put a little slash to indicate there's no change in area. That means there's no difference in the velocity between any 2 points in the tube either. The velocity is constant. V is constant.
Sorry, are we able to ask questions?
Yeah, absolutely. Go for it.
So continuity only holds if the area is the same throughout, correct?
So, so not quite. So the area being the same throughout tells me that velocity is constant by continuity. Continuity itself holds as long as there are no like leaks that we aren't keeping track of. So, for example, let me try to draw a picture. So continuity is a statement of volume conservation. So if I have 2 points between, say, here's my initial point and here's my final point, and the area can change, whatever, various parameters of the fluid can change. If my tube doesn't have any leaks between this initial and final point that I'm not keeping track of, volume will be conserved. So continuity is fine. In other words, I'm not losing any volume of my fluid. However, if, say, I had just like a leak out here where the fluid is free to flow, then I'm going to lose some of my volume. And so continuity won't work as much. Like if I had 15 gallons per second coming in on this side, 15 gallons per second, or 15 meters cubed per second on this side coming in, and I don't have a leak, then I would need to have 15 gallons per second coming out on this side. If I did have a leak, then maybe I'm losing a gallon per second here. Then I'd be having 14 gallons per second on this side. So the fact of the matter is, as long as I'm keeping track of all of my fluid flow between points, between my initial and final points, then continuity is conserved. Like I have volume conservation. So if I were keeping track of this 1 gallon per second, plus this 14 gallon per second over here, I still have 15 gallons per second. Okay. Does resistance impact velocity? Very good question. Does resistance impact velocity? Resistance, what I would say is that in a closed pipe, resistance does not impact velocity. We'll try to do some intuition builders there. Yeah, so, but that needs some more motivation. Got another question. Does this mean continuity always holds as long as there's no leak? Yes, essentially. Continuity always holds as long as there's no leak. As long as we're keeping track of where our water is going, continuity holds. Another question. Is speed dependent on the potential of gravity at all in the fluid, or is pressure the only value that changes with a change in gravity? So what I'd say is that it depends a little bit on your system. So we'll see a bunch of different examples. I'm sorry, I know it's very general. We'll see a bunch of different examples. Yeah, so speed can be dependent on the potential of gravity. It's primarily dependent on volume. So in closed pipes, here's what I'll say. In a closed pipe with no branches, speed is dependent on area. That's what I'll say. In a closed pipe with no branches, the speed in any given section is dependent on area. Life can get a little bit more complicated. Yeah. Okay. All right. Let's keep on moving. Good questions all. So we have continuity. We have the Bernoulli equation. Let's finally hop in. So first off, a 7B student observes the water levels in 3 columns. She notes that the measurements for each column are either 3 or 4 tick marks. Hopefully this is legible now. Might have had to zoom in there. She observes that the levels in each column are either 3 or 4 tick marks. Mark the columns with their appropriate values, show your work, and explain your answer. Okay, so let's look at our fluid system. All of these tick marks must be marked with either 3 or 4 ticks. 3 or 4 ticks at each of A, B, and C pressure sensing pipes. So let's motivate. I'll just say for now what these pipes do, and then I'll encourage you to check out your DLs to figure out like exactly why. So roughly what I'll say is that the pressure in the tube increases the higher the pressure, or the higher the height of these pipes. Let me go ahead and lock some stuff real quick. There we go. Okay. So roughly, the way I think of it is like this. So to give a little bit of background theory before I hop into the intuition here. If I've got some fluid flowing through this lower pipe, there's a kind of interface between the fluid flowing through the lower pipe and the fluid which is just hanging out at the top of this, in this pipe here, in the, what I'll call the gauge pipe, the vertical pipe. So pressure pushing upward from this lower pipe is what causes the fluid to stay tall in this upper pipe, what causes the fluid to fight gravity and stay up in this upper pipe. Okay, so that's to say that it turns out that the difference in height from the top, or not the difference in height, sorry, the difference in pressure from the upper part to the lower part of this gauge pipe is rho g h, where h is the height of the water column, the fluid column. So rho is the fluid density again. It's the amount of mass per volume for the fluid, in this case water. G is gravity, 9.8 meters per second squared, and h is the height of that column. So what these do is they give me a handle on pressure. This question, 3 or 4 ticks, and which of these pipes has 3 versus 4 ticks, is really asking me, what is the, where is the pressure highest and where is the pressure lower? Okay. So this is kind of an intuition building question. We don't need too much math here. So the first thing to note is that between this first section and the second section, 1 and 2, there is a height change with no resistance. So if I just look over at my Bernoulli equation, which terms are going to change? Between points 1 and 2, which of these things changes? Well, I do have a height change. Again, the cross-sectional area of the tube is constant, so I don't have a velocity change. The velocity is going to be constant throughout. I don't have a pump between these 2 points. There's no pump. And I don't have any resistance between these 2 points, 1 and 2. So there's no resistance. Okay, well, I've ruled out 3 of my 5 terms, and I know that one of them changes. So the other one must also change. Pressure must also change. Sound good? Still on the same page? Okay, sweet. All right, so my height is dropping. So if I were to have, that would mean a delta y that is negative. So I've got a decrease in height from point 1 to 2. In order to balance that out so that these 2 terms sum to 0, since the other terms are all 0, delta P must be positive. I must have an increase in pressure going from point 1 to point 2. So that means that this one, the first one, should have 3, because there are either 3 or 4 tabs, or 3 or 4 ticks. And the second one must have 4 ticks, 1, 2, 3, 4, because it's at a higher pressure. We've got a hand raised from Alice, I think. I don't know, that might be left over from before. Question?
Oh, my bad. I will take that down.
You're good, no worries. Okay.
Sorry.
Question. Go for it. Yeah.
So at the interface point, within your fluid system, is that technically considered part of both your gauge and also like that lower fluid system?
You're saying here, this section, this interface?
Yes.
So this is a good one. I would say that basically these are 2 essentially separate fluid systems in the sense that they don't exchange current at this stage. Like there's no fluid flowing up into this pipe when they're at equilibrium. So they're separate in that sense. However, one of them is clearly pushing on another, right? Like they're pushing against each other. So in that sense, they are together. So to put it in like a single sentence, what I'd say is they are separate fluid systems, but they interface via pressure. Like they have a link between them, which is pressure. They're separate fluid
Okay.
systems in the sense that there's no current flow between them. They're linked by pressure.
Okay, thank you.
Yeah. Thanks for the question.
I have a quick question also.
Go for it, Diego.
So we know that so B is higher pressure because we determined that pressure is positive.
That's right.
Okay.
So change in pressure from point 1 to point 2 is positive. So because the change in height from point 1 to point 2 is negative, like 2 is below 1, that means rho g delta y is going to be a negative number. Final minus initial there. The height of 2 minus the height of 1 is going to be a negative number. And in order for the Bernoulli equation to balance out to 0, or in order for it to balance, I guess you say, because all the other terms are 0. So in order for these two to sum up to 0 to equal the right-hand side, that means the change in pressure must be a positive number equal in magnitude to rho g delta y.
Makes sense.
Okay, cool. Thanks, Diego.
I have one question.
Yeah, go for it.
Where did the delta P equals rho times gravity times height equation come from?
Up here? Good.
Yeah, up
Okay.
the top.
So this is a bit of a doozy. So here's a couple of things I'll say. So if we just examine this upper tube, so the tube where no current is currently flowing, it's just kind of standing there. Water's just standing up there. The pressure at the upper point and the pressure to the lower point is what I'm interested in. So yeah, so this is where it's like coming from, is I'm trying to figure out the change in pressure from the top point of the gauge to the bottom point of the gauge. This is why we call it the gauge pressure. The absolute pressure, which I will say and only motivate a little bit, P absolute at the bottom of this upper tube is going to be the atmospheric pressure plus delta P plus rho GH. Rho GH. This is the absolute pressure. So as far as where it came from, I'll just say, because I know we're getting a little short on time, I want to make sure we at least get most of the way through at least one quiz. I'll just say is related to taking the Bernoulli equation and applying it between these 2 points. So if you take the Bernoulli equation and apply it between these 2 points, you'll end up finding this to be true. The change in pressure from the upper point of the gauge to the lower point of the gauge is rho GH. Is that okay for now? Yeah, thanks, okay.
Thank you.
Okay, so any follow-up questions?
For the ticks, how did you determine like there's 3 versus 4? Is it because they have to be equal?
Sure. So the reason that I know it's either it's given in the problem, it's either 3 or 4 tick marks. I determined that the first one is 3 and the second one is 4. Like I determined that the relationship between them, because I know that the pressure in the second one is higher than the pressure in the first one. So since the pressure in the second one is higher than the pressure in the first one, the second one must have the 4 ticks. It must be the one that indicates higher pressure. And the first one must have 3 ticks. It must be the one that indicates lower pressure.
Okay, that makes sense.
Yeah, good.
So if
thanks.
if the pressure was negative, so like it was going it was an up, like going up instead of a downgrade, you would then have a delta P that's negative, and you know then that B would be smaller.
That's right. So if we were to go up instead of down, our answers would be reversed. Yep, for this one. Okay, there was another question. What was the p-value for the delta P equation again? So I think you mean this guy here, the squiggly P. That's rho, that's mass density. So rho is mass per volume. It's the density you're probably most familiar with. Okay, so we've got the first part done. We know it's 3 ticks at point 1, 4 ticks at 0.2. And now all we've got to think about is this last one. So now what I'd like to do is think about the Bernoulli equation in the context of moving from 2 to 3. So I'm going to erase some of my squiggles. There we go. Okay, so now let's think about 2 to 3. 2 to 3. We're moving from 0.2 to 0.3. All right, so as I move from 0.2 to 3, notice now that there is a resistance in my pipe. I have R greater than 0. Resistance is now in my pipe. So the resistance term will be here. There is no pump between points 2 and 3. So E pump per volume is 0. There is no change in area of my pipe. So there will be no change in velocity or velocity squared. There is no change in height between points 2 and 3. And finally, well, again, I've got 3 of my 5 terms equaling 0, and 1 of them is non-zero. So the last one's also got to be non-zero. Otherwise, I'd have some number equaling 0. So I must have a change in pressure, and I must have and I do have a resistance. I know that. Okay, so let's just rewrite that up here. Delta P equals negative IR. So I have a positive resistance. There's no such thing as negative resistance for our purposes. You can kind of think of a pump as negative resistance, but maybe more on that later. So okay, so a resistor is going to have some resistance. We've got some current flowing through it. So on the whole, pressure is going to decrease as we go from 0.2 to 3. Resistors typically act to decrease pressure. So within a closed pipe, resistors act to decrease pressure. So I'm going to have a negative number associated with loss, thermal loss. And delta P will, as a result, need to be negative in order for our two numbers to equal each other. So that means that the pressure at 0.2, pressure 2, must be greater than the pressure at 3 in order for delta P to be negative. In other words, this C tube must have pressure marked by 3 tick marks. Okay, I've got a couple questions rolling in. Let me look. We've got Ethan asks, how do we know the second tube has more pressure? Aren't the tubes the same height? Just the second is relatively shorter because the tube slants down. So good. So Ethan, the points we're considering are actually points 1 and 2. So points 1 and 2 are inside of this little lower, more horizontally inclined pipe. So the pressure at points 1 and 2, these ones are different. The pressures at the top of the vertical tubes are just atmospheric pressure. Yeah. Okay, hopefully that helps. Jordan asks, are I and R always positive? So R will always be positive, yes. Current is positive as long as you take the direction of, as long as you take the final point to be downstream of your initial point. So if you take your final point to be downstream of your initial point, current will always be positive. So here, for example, I needed to have defined my delta P, my delta in general, for from 2 to 3. My delta P would have to be P3 minus P2. That's final minus initial. So the final point is further downstream than the initial point. As long as we define our current to be in the direction of downstream, like final minus initial to be the final point further downstream than the initial point, current will be positive. Okay, how did I determine the tick marks? Go back and look at it. Sorry, Tim. So the tick marks I determined by applying Bernoulli's equation between each of these points. So between 1 and 2, and between points 2 and 3. Okay. Oh, I see. Oh, yeah. Sorry, Tim. If you were asking, how do we know it was 3 or 4? Yes, that was given in the question. Sorry about that. Okay. All right. Cool. 3, 4, 3. Let's hop on down to B. The flow rate at position 2 is given by 3 meters cubed per second. So what's that telling me? Flow rate is the same as current. I is 3 cubic meters per second. The resistance R between 2 points, about 0.2 and 3, is 2,000 joule seconds per meters to the 6th. What a weird unit, right? So here's R. Calculate the height difference between points 1 and 2, show your work. Okay, so good stuff. What we want to do now is figure out the, I guess, by figuring out the pressure difference between points 1 and 2, we'll have a handle on the, what is this called? The height difference. So let's try to do that. So delta y between points 1 and 2, if you recall from our previous argument, using the Bernoulli equation, these three final terms, the kinetic term, the pump term, and the resistance term between points 1 and 2 are 0. So the change in pressure from 1 to 2, or also, yeah, I'll just say 1, 2, is going to be negative rho g delta y, where delta y is going to be a negative number. So overall, this thing is going to be positive. And the change in pressure from 2 to 3 is, let's see, it'll be negative IR. There we go. That's from our 2 previous applications of the Bernoulli equation to our, what do you call this? To our system between points 1 and 2 and points 2 and 3. So one other little handy trick that we can use is if I look at the tick marks, I notice that the difference in pressure between point 1 and point 2 is the same magnitude-wise as the difference in pressure between point 2 and point 3. How do I know that? I know it because these 2 gauges between 1 and 2, I have a 1 tick difference. So there is a 1 tick difference in height of the gauge between 1 and 2. That indicates a pressure difference. I have the same number of ticks, the same height difference between gauges 2 and 3. So I go up 1 tick versus down 1 tick. So the difference in pressure between 1 and 2 is the same magnitude-wise as the difference in pressure between 2 and 3. That tells me that, again, so I'll just write that down. So because of ticks, because of the equal tick spacing, 1 to 2 versus 2 to 3, these 2 changes in pressure are the same. 2 changes in pressure have the same magnitude. I'll try to scale that up a little bit. I'm not sure it's visible right now. Oof. Let me move it over. Okay, because of the equal tick spacing, the 2 changes in pressure have equal magnitude. So to write that down mathematically, that means that the size of this thing, magnitude rho g delta y, is the same as this thing, magnitude IR. Okay, so to find the height difference between point 1 and point 2, that's the delta y. To find the height difference between 1 and 2, I can just solve for delta y. Delta y is going to be whatever the positive version is of IR over rho g. And these numbers should all be positive, so it should be good. Okay, so now I can solve. Let's do that. Delta y is IR over rho g. I is 3 meters cubed per second. R is 2,000 joule seconds per meters to the 6th. I'm going to be cavalier with units because I know it's already getting kind of cluttered. And rho g is, well, it's water. So rho is 1,000 kilograms per cubic meter. Matching up my units here. I'm using meters, not centimeters. And gravity is 9.8 meters per second squared. Or if you use 10, you should be fine. Yeah. I use 9.8 because it's been too thoroughly ingrained. But if you use either 9 or 10, or 9.8 or 10, we'll take both. Okay, so when I run that in my calculator, I get 0.612. Anybody else back me up on that? So by solving that, I get a delta y of, or I'll just say height. Really, if I'm talking about truly delta y, so 0.2 minus 0.1, it's going to be a negative number because we drop. So I'll say negative 0.612 meters. Sorry, I might have missed this. A question. Sorry, I might have missed this, but why does the pressure change in 1 to 2 equal that between 2 and 3? Okay, good. So the reason that the pressure change, the magnitude of pressure change from 1 to 2 is equal to the pressure change between 2 and 3 is because the number, how do I say this well? The gauges, the pressure gauges, these vertical pipes, change by the same number of ticks or the same height. So in 1, we have 3 ticks. In 4, we have 4 ticks, which means we went up 1 tick in pressure. From 2 to 3, we go from 4 ticks to 3 ticks, which means we went down 1 tick in terms of pressure. So both of them represent a change of 1 tick. Jordan asks, why is the number negative if the height increases? So I think this is probably conflating the height of the gauges with the height of the fluid that we're interested in. So when I say that the height decreases, I'm saying that the vertical height of 0.1, so like let's say I draw in, let's put a ground in. Here's my ground. The vertical height of 0.1 is greater than the vertical height of 0.2. So the height actually decreases here. 0.2 is this lower point. 0.1 is the higher point. So it's not about the height of the pressure gauges. The height of the pressure gauges just tells me about pressure. Thanks for your questions. Alexandria asks, what's the value I wrote down? I wrote down negative 0.612 meters, and I haven't checked that against the notes, so hopefully I didn't make any calculator mistakes. Why do we absolute value? You don't have to absolute value. If you don't, so for me, here's what I'd say is like, for me, it's easy to think about it in terms of the magnitude of the pressure changes. So I know that in terms of magnitude, these pressure changes are the same, and I just like to do things in terms of magnitudes where I can. You could also just say, so if you wanted to totally just nix thinking about the magnitude, instead what you could do is solve it by saying delta P 1 to 2 is equal to negative delta P of 2 to 3. So I have an increase in pressure from an increase of pressure 1 to 2, and a decrease in pressure from 2 to 3, and they're the same size. Why do we absolute value? Yeah, okay, was the rho value given? We will be giving the rho values, yes. So regardless of whether it was given here, it looks like it was, yes, given here, but we will be giving the rho values. Can I show the calculation of units? My units aren't coming out right. Yeah, let's do that. Let's double check. So let's double check. Delta y is, so 3 meters cubed per second for the speed. So it'll be meters cubed per second for the first term, speed, times R is going to be 2,000 joules times seconds per meter to the 6th, divided by rho, which is 1,000 kilograms per meter cubed, times g, which is 9.8 meters per second squared. Okay, so what cancels? Let's look. Seconds are going to cancel here really quickly. I'll X them out like this. X, X. I can cancel this meters cubed with, hang on. Okay, this meters cubed and this meters cubed together will make a cancellation with this meter to the 6th. So what do I get? I get, so 6,000, I'll just put the number in, it's 0.612 and then I have joules over kilograms times meters. I'll flip the second squared up. Joule second squared per kilogram meter. So what's a joule? A joule is a unit of energy. So I think of it as force times distance, which is mass times acceleration times distance. So it has units of kilograms times meters per second squared times meters. Okay, so what do I have? The joule gives me kilogram meter squared per second squared times second squared over kilogram times meter. Second squared is going to cancel. Kilograms are going to cancel, and the meter is going to cancel with the exponent to give me 1 meter. There we go.
Sorry, I'm having a hard time finding it, but where does it say rho is 1,000 kilograms per
Good.
meters?
So I snipped it off in my casual snip, but it's at the bottom of the page on quiz 1-1. So
Oh, okay. Thank you.
yeah, and we'll do the same on our quizzes. We'll include we'll include useful constants and such on the bottom. Sorry, not on the quiz, but on the midterm, or rather, we'll put it on a backside sheet. Okay. Last part. Sorry, I know this took a little bit longer than I originally planned. Let's discuss the very last part, and then we'll get on out of here. I'll take final questions for maybe 5 or so minutes at the end if there's more things you want to talk about. In a new scenario, the water is flowing to the left. The resistance between point 1 and 2 is now the same value R as the resistance between points 2 and 3. Okay, so we've got now new resistance. The flow rate, height difference, the value resistance of R, the value of resistance R, the area of the pipe is the same as in question 1. The measurements of column C is 4 tick marks as shown. Nice. Mark the levels on the remaining fluid columns, show your work, and explain your answer. Okay, so the first thing is, and again, we've only got about 5 minutes, so this first part I'm going to do just kind of intuitively and check that the math works. In the first part, if I look again at my Bernoulli equation, I've got the same current, I've got no change in height, I've got no pump, and I've got no change in surface area. So because the resistance is the same and the current is the same, and there's no height difference, I have the same drop in pressure that I had in the previous scenario. So because everything's the same for 3 and 2, like between 3 and 2, except for the direction of current flow, the magnitude of pressure drop is the same. We're going to have the same drop in pressure. So we're going to drop a tick here. And again, that's the kind of thing you can show rigorously using the Bernoulli equation, but since we're a little low on time, I'll leave that. It's the same exact calculation type as we did in question 1. Okay. Measurement of the column C is 4 tick marks as shown. Mark the levels of remaining fluid columns. Show your work, explain your answer. Okay. So the one that I will show work for is this one from 2 to 1 because it's a little bit more complicated. So I'm now interested in the change in pressure from 2 to 1. So my final point is 1. My initial point is 2. That way I line my current up with the direction of my initial and final points. Final points should always be downstream of initial points. Okay, so if I look at the Bernoulli equation, between those 2 points, I do have a change in height. I do not have a change in speed because I don't have a change in the size of my tube, the cross-sectional area of my tube. I don't have a pump, so that'll be 0. And I do have resistance. So now my formula looks like delta P plus rho G delta Y equals negative IR. Delta P plus rho G delta Y equals negative IR. So negative IR from the previous part corresponds to 1 tick. I've got the same resistance, I've got the same current, so that's going to take away 1 tick's worth of pressure. This corresponds to losing 1 tick of pressure. Losing 1 tick of pressure. Meanwhile, rho G delta Y, now I'm going up. So instead of increasing my pressure like we did when we went from the higher position to the lower position, 1 to 2, now our pressure is going to decrease as we flow uphill. So this is going to correspond to losing 1 tick as well. So it may not be immediately clear why it's 1 tick in both cases. The reason it's 1 tick is because in the previous parts, like it's 4 reasons discussed in the previous parts. So going down with the same current and 0 resistance over here corresponded to going down 1 tick. Yeah, similarly, going from the region of no resistance to the region of positive resistance over here corresponded to dropping 1 tick. Okay, so that's to say that this final one will have 2 ticks. Oops, it'll be 2 ticks off from the previous one, so it'll be 1 tick at the end. Okay. I got a couple chats coming in. Let me give them a look. Class end at 8:50. Formally, yes. If students would prefer that I make it a really hard cutoff at 8:50, I definitely will. Because they're being recorded, I don't mind people leaving at 8:50. And then if you want, coming back to look. Isn't 0.3 at 4 tick marks? 0.3 is at 4 tick marks, yes. Yes. Y is PG delta Y if there's no change in height. There is a change in height between 0.2 and 1. That's what I was interested in for the second part. Where will the recording be posted? It'll be posted under Zoom meetings, cloud recordings. I have to leave for Chem Lab, but just wanted to say thank you for staying instruction. Oh, thanks. Oh, okay, it's probably gone already. Thank you. Okay, if height is increasing, wouldn't we gain 1 tick? So if height is increasing, I lose a tick. So the reason for that roughly is that when I increase height, my fluid has to expend some energy to go up the hill, so to speak. It's got to expend some energy to go up. And if we examine the Bernoulli equation and see what things are allowed to change, only the pressure must be, only the pressure can contribute to that increase in height. Okay, so you know it was 1 tick because of the previous analysis, right? Yes, that's essentially true. I know it's 1 tick because of the previous analysis. If I wanted to double check, I could always do the analysis again. But live on a quiz, yeah, making those kind of connections is a good idea. Or live on an exam rather. Ethan says thanks. Oh, thank you, Ethan. All right, what does it say under PG delta Y? Under rho G delta Y, it says losing 1 tick as well. So that's to say that the change in height also corresponds to a 1 tick loss in pressure. 1 tick loss in my pressure gauge. 1 tick as well. Could you maybe go over unit conversions for number 2 quickly again? Let me wrap this up real quick and formally end, and then I can talk about unit conversions again. Height decrease.
Can I ask one question really quick?
Yeah, go for it.
So as a general thing that we did for this, for the last one, we lose a tick from going from 2 to 1. Now that we have resistance, we lose a tick to resistance and we lose a tick to height, right?
That's right. Yep.
Okay, thank you.
Sure.
I have a question. Could you explain, like, is that always the case that if height is increasing and which height is increasing, and how does that correlate to losing ticks?
Yeah, so this, I'm trying to think of a way to say it very succinctly, but still clearly. I don't know if I have a good one. So what I'll say is this. Each of these points 1 and 2, are referring to points 1 and 2 are referring to points in the lower fluid system. And yeah, and we're pretty much dismissed. So if y'all are waiting around, feel free to head out if this doesn't interest you. So each of these points, 1, 2, 3, are the points where we're interested in the pressure. These vertical tubes just give us a hint about, or they measure the pressure. So when I refer to delta y is always, or delta y in the context of the Bernoulli equation, delta y is always referring to height differences, like inside the fluid system, height distances of the points being measured. Does that answer or not quite?
Because I'm just trying to understand, like, so the current for this one goes to 1, correct? Like it's going in the direction where 1 is going.
That's right. It's going from right to left.
Yeah, so then if it's, I don't know, I'm really confused because it made sense in the first part, but now I'm kind of, like, I don't understand why we wouldn't be gaining instead of losing.
So, oh, I see. Okay, good. So I think I maybe see what's going on here. So the fluid system, like the lower part here, is gaining height. It is definitely gaining height. So delta y from 2 to 1 is a positive number. So maybe I should rearrange this. So delta p from 2 to 1 is negative IR minus rho g delta y. Oh, I need to put a g in there. And delta y is a positive number if we're going from 2 to 1. So delta y is positive, but the change in pressure from 2 to 1 is negative. We're losing pressure as we go up. And yeah, hopefully, I mean, if you live in a house where...
That makes sense.
Okay, good.
Yeah.
Nice. The upstairs always has worse water pressure than the downstairs. You know what I'm saying?
Yes.
Yeah. Okay. All right. So height decrease usually means pressure increase while vice versa. Yes, that's roughly that's a good rule of thumb. Although again, you should always double check it to make sure that the assumptions of the Bernoulli equation are in check. I think I'm going to call it there in terms of the recording, and then we can go back and chunk through the units again. Sound good? So unless there's one more follow-up.
Sorry, could you quickly explain why you know it's 1 tick for each? I understand why they're both negative, but how do you quantify it as 1?
Sure. So each of these, let's put it this way. So I know from the very first problem that there are that the pressure changes corresponding to moving from high to low and from the non-resistive area to the resistive area, those each correspond to 1 tick. So 1 tick of pressure change. So basically I carry that knowledge down with me. Because the current is the same in the third part and the first part, and basically everything is the same except for fluid flow and the addition of another, except for fluid flow direction and the addition of another resistor here. I know that resistance changes, so a section of resistive pipe corresponds to 1 tick, and I also know that this height change corresponds to 1 tick. It's really just a question about the direction at that point. Does that help or not really?
Yeah, that helps. Thank you.
Yeah, sure thing. Okay, so I think I'm going to go ahead and end the recording, and then we can go back and quickly hit those units. Let me do that. All right, thanks for tuning in if you're coming to us from the future.